Hello, everyone. Welcome to this week's Crunch seminar. As every other week, this week also we have two talks. Our first talk is by Professor Xiliang Lu. He would be talking to us about a Gaussian mixture distributive based adaptive sampling methods for pins, which he has acronymed as GAS. He is a professor at Wuhan University. He received his bachelor's degree from the School of Mathematical Sciences, Peking University, and obtained his Masters of Science and PhD from NUS Singapore. Afterwards, he held research fellowships at NUS and served as a visiting scholar in the University of Maryland, and also worked as a postdoctoral researcher fellow at the Radon Institute of Computational and Applied Mathematics. He joined the School of Mathematics and Statistics at Wuhan University in 2010. His research interests include computational and inverse problems, scientific computing, and machine learning. With that, please join me in welcoming him for today's presentation. Thank you. You may want to take it away.
Okay, thank you for the nice introduction. And also, I'm very happy to have this chance to present our recent work in this current seminars in Brown University. The talk is the Gaussian mixture distribution-based adaptive sampling method for pins, which is basically to find a adaptive sampling way to connect a point for the pins. Okay, all right. This is a joint work with some professors and students in Wuhan University, with Yuning Jiao and Zhijian Yang is a professor in my colleagues, and Li Di is a PhD student, and Yuan Chen is a postdoc. So this is outline of our talk. So firstly, we should know that solving the partial differential equations is one of the very fundamental tasks in all kinds of science and engineering problem. There's a lot of kind of a problem we need to solve. For example, the Poisson equation, Laplacian, the Hit equation, or some more complicated Navier-Stokes, Schrödinger, or Maxwell. A lot of partial differential equations in different applications. But unfortunately, most of them do not have closed form solution. We need to solve it numerically. In the last like the 70 years, the numerical solution to the partial differential equations have been developed well. For example, we have the finite difference method, finite element method, and also other methods. Okay, but for this about a few years, the deep solver, which is we to try to solving these partial differential equations by the deep neural network, okay, has very popular. There's a lot of papers to focus on these things. Here I list some very famous deep solver. The first one is the Wuhan is the deep race method. And also most popular one is George's work is the pins, okay. And also there's some others, deep Gaussian or the weak advisor network. This is based on the different formulation of the partial differential equations. Even mathematically, they are equivalent. For the pins, which basically depend on the least square form. Okay, there's I believe every people very familiar with the deep neural network, so I just go through it very quickly. When we talk about the deep neural network, we actually thinking as this kind of approximation of the function, which is one network is the composition of this simple maps. So the T here are a phi transform, and this sigma is a component-wise nonlinear active functions. Okay, when we're talking about the deep neural network in our talk, we actually say it is functions, which is just as is this composition form. The active function can be chosen as the logistic, or the ReLU, or the others. Okay, and to train this problem, because when we use a deep neural network, we always rewrite the problem into a nonlinear optimization, and we need to train it by some optimization algorithm. Stochastic gradient descent is one of the most popular one. Okay, for the applications, the most successful application for the deep learning is discriminative learning, like the classification or regression. Okay, and also the generative learning, which is try to learn this density from samples. Okay. Also, we focus on the deep solver for PDs, just try to learn a function. We learn a function from the different equation and some sample points. So we need two things: we need the equations, we need the sample points. There's also other applications there. For this deep solvers, when we have the deep solvers, we always need, always want these deep solvers performance good. Okay, that's what, if we're concerning about the error of the solution, the target solution and our numerical solution, basically it can be decomposed as three parts, which is called approximation error and the generalization error and optimization error. Okay, for the optimization error term is always be difficult, and it's not our we do not focus on it much. Okay, because the find any method is very popular and we have already understood this method well, so we can employ the idea from the find any method to help the deep solver. So if we concerning the find any method, we know we need to consider the result projection, which is causes the solution between the find any method and the real solution. And also we can do the integrations not actually, and also the linear system can be solved iteratively. Okay, for the deep solvers, which is also have the three parts, they are not equivalently one corresponding, but we can have this approximation error plus generalization error more or less like the risk projection. Okay, but for the file element method, we know there's called the adaptive file element method is to construct a problem based mesh, which is can get the solution more accurately. So we want to use this some similar idea to get this adaptive sampling method for the pins. All right, so let's look at the pins. The pins, the original idea for the pins is quite simple and straightforward. It's like we want to solve in these partial differential equations. We have this equations on this inside the boundary and inside domain and the boundary conditions. We just taking the least square. Okay, so with the loss of the pins is just like we taking the least square inside the boundary, inside the domain, and taking the least square on the boundary. We just add them up. Okay, if we get this loss function, and we can train it. But this is integration. So to approximate this integration, we just using the Monte Carlo approximation. Okay, so basically the pins is more or less like we have this least square form of the partial differential equations and plus the Monte Carlo approximation. Okay, but the key issue is how to we get in this point. The original pins with the proposal, which is static pre-sample data set, which is more or less like the uniform distribution inside domain or the outer boundary. Okay, but of course, if the solution is not so smooth, the solution if have singularities, okay, can be a point singularity or line singularity. Okay, if the solution have singularities, the pins will be not so efficient. Okay, because it do not have the way to catch this singularity. Okay, to overcome this kind of the difficult, there's a lot of adaptive sampling method has been proposed. For example, the Lulu proposal is RIR and RAD are all residue based, which is one is the refinement, another is the distribution. Okay, basically it's like we have the large value on the residue, then we put more points. Of course, the idea is very straightforward and is powerful. Okay, and another one is the Xiliang. He proposed called the selection net. Okay, is based on the weighted least square. Is just changing the pins, the formulation for pins a little bit. It's not only taking this Monte Carlos, is taking as some weight, and this weight is we'll see is very similar as our approach letter. Okay, but he uses another network for this weight. Okay, and thus is to introduce a variance reduction by the importance sampling technique and getting another network to train to train these density things. And another work is about the Zhou Tao proposal called factual informed adaptive sampling for pins, which is also used as a residue. That says when the residue is big enough, and we put more points. It's small than some tolerance, so we just ignore that. Okay. If we see this all the existing work, we find that most of them are using the residual information. Of course, we also use it. The residual information is very important. Okay, and some of them have the additional network to train, which is makes this whole work a little bit complicated. So there's a lot of ways, but we want to find, can we put all the and understanding all these methods in a unified framework? Okay, then we maybe can find a better way to do this adaptive sampling. Okay, so that is our goal. We want to provide primarily effective and easy to implement method. We want this method is easy to implement and it is efficient. Okay. So we start from the realization of the pins. For the original pins, we know it's the least square, just have the least square. But there, we should know this. If we looking at the partial differential equation itself, we know it is zero. The residual term when the solution, when we take the solution of the PDEs, the residual is zero. When the residual is zero means we maybe not take the integration in the bigger sense. We can take integration on any distribution. So we just do some realization to the pins. We introduce this the density function rho. Okay. So this is our cost function. We not only have this x, which is the solution. Okay. We also have this rho. This is another the density distribution. So that means we want to get this the solution u and rho simultaneously by solving the kind of minimax problem. Of course, the minimax problem is just not exactly solve that. We will explain a little bit later. Okay, but most likely we're solving this kind of the minimax problem. So we have the u, we have the rho, we have the two qualities. One we call it the prime thing, and it's a dual things. It's just like the optimization when we talk about the minimax, we always have prime and dual stuff. All right. To solving this kind of minimax problem, then the most popular way is to update alternatively, or called the Wuhan method. Okay, that is we have the update this u and the rho separately. If we have the rho, then we can update this u by like the gradient descent or other optimization problems. Okay, because we have a square quantity, so it is not hard to find the good approximation of the UK plus 1. Once we have the UK plus 1, we use a dual accent to the rho subproblem. So dual accent means we can just update this rho. This is new things solving this maximization problem approximately. Then we with a certain step size of k there. Okay, so that's it. Basically, this is the Wuhan type method. We have the gradient descent on the prime variable and the dual accent on the dual variables. Okay, so we try to understand the other sampling algorithm to put in this framework, but not exactly same. We're using this DAS and FI pins for examples. Okay, for DAS, basically this UK plus 1 is just solving this the prime the minimization problem when we have the rho. Okay, but the rho there is is take the maximization problem is not the similar form. It's taking the minimize the K divergence between the rho x and another. This is the residue from the residues and not distribution. Okay, this is DAS. And FI pins is U star problem is also similar, and the rho star problem is just like the residue is large, then we can put the density is there. But when the residue is smaller than tolerance, we just ignore that. Okay, this FI pins. Okay, now we moving back to this the rho direction. To iteration of the rho, this is the most important things. How do we find this the argomax problem? Unfortunately, if we just look at the argomax problem, if without any constraint on this rho, we know this optimal solution is like direct data distribution. It's acting on the maximum point of the U. Okay, on the maximum point of the x. When this residue is large at one point, then rho just concentrate on this point. Of course, this is not what we want. Okay, so that means to make the whole things workable, one need a regularity assumption for rho. This is very artificial. Okay, every people can use their own assumptions. In our work, we restrict our regularity assumption as follows. Okay, we just assume this density function is nothing but the Gaussian mixture. We're choosing the Gaussian mixture for several reasons. First, the Gaussian mixture is can approximate any distribution well. And also Gaussian mixture is the things we can handle this very efficiently. So here we just assume this the rho in this class is the ng of the mixture of the Gaussians. So there's only so at each iteration step we just need to verify with this pi and mu and sigma. Okay. So how do we determine? We're using it by some of the density estimation or Laplacian approximation. Okay, to explain the idea more clearly, let's concerning the one-dimensional case first, and with only one Gaussian, it's no mixture, only one Gaussian. So we explain how do we find this the parameter from this residual function. Okay, if in a one-dimensional case, this is only one Gaussian, so this is the things we want. We want to compute this mu sigma and mu star and sigma star. Okay, because we know this x0 is the maximum point of the R, so we concerning this V is nothing but the minus node. Okay, then this R can be do the expansion just nearby the x0, and we know because the x0 is a maximum point, so the R prime and the V prime are both be 0. Okay, so the V prime is 0, so that means this R is not, it can be approximated by this quantity. That means this mu sigma, this mu star and sigma star can be approximated by these two things. Okay, so basically mu is nothing but x0, and sigma is the V double prime. And the V double prime can be further approximated by the V prime, by the R prime, and the R itself. And so that gives us a very crucial idea. This position x0 position is the mu, and the variance here, which is nothing but the R prime. Okay, this gives us the very crucial idea. And how, so for the multi-dimensional, multi-peak and high-dimensional case, and we say, oh, okay, we can take the maximum point of the residual function. Okay, we have the residual, we take the maximum point, and with which will be which will be our mu. Okay, and this max can be we will see later. There's two different ways to choose it. One is globally, another one is locally. And how do we determine this the correlation matrix, which is nothing but we taking the derivative of this R, and we just diagonal matrix and taking inside the inverse. Okay. So compare with the all the existing method, this the similar thing is we have this we know we added add point on this when the residue is large, but we also know how to control this the covariance. Okay. How large of this point in fact, that is the using the Gaussian mixture will help us to get the much clearer landscape of this the residue distribution. All right. So once we have this mu and the sigma, and we can do this kind of the iterations. If we combine all these things together, we have this algorithm. We want to explain in more details. This is called the Gauss algorithm. So Gauss algorithm involving we are adding this point and each time we added some sample points. So basically, we have this the originally we using the normal we're using the uniform distribution, and every time we adding M1 interior point and M2 the boundary points. Okay, how do we add this interior point? We just calculate the residue. Okay, it can be as the globally just taking the ng top terms or the local maximum. We just when we catch up one maximum, then we have the ball, and all the other maximum point can be outside of the ball. They call the local maximum points. We have these are two versions. They are slightly different. Okay. Once we have all these local maximum or global maximum points, then we can construct this the Gaussian distribution and generate this all these points from this Gaussian distribution. We add all this the new sample point and using all this the previous one. So basically that means R of k. If we remember this R of k there, this R of k means it will be changed during the iteration. Okay. All right, your R of k becomes smaller and smaller. Okay. So for the inside, it's just using the SGD to train, because it's nothing but the pins, but we just have the different sample points. When you have more and more sample points, we just train these pins by the fixed epoch. All right, so that's our algorithm. Let's see the numerical examples. So we start from this one peak problem. Okay, so this is the benchmark test problem. We have the one point singularity here. Okay, so this is the exact solution. We have the point singularity here. Okay, now this is after one iterations for gas, which means we have the 500 point, which is uniform distribution, and we add points after one iteration. Every time we add in the 500 points here. So after y iterations, that will be the distribution. Okay, and the error is still be large. Okay, and after five iterations, now that's mean every inside the pins we just train the 3,000 times. Okay, so after the 5 iterations, it's adding point or constraint on this singularities. So the error is decreasing to the maximum error to the 0.03. Okay, we can find the most point are concentrated on these singularities. Okay, after 5 iterations, after 9 iterations, though that means all the points, all the number of the samples are 5,000. It's a very concentrated, and the error is very small already. It's maximum error is 0.01. Okay, that we can see is for after the 300 points, that means after the 5 iterations. This is the uniform data. If we use pins for uniform data, this 300 points, it just look like that. But if we're using gas, this is 3,000 points that look like that. All the ending points are concentrated on this the singularities. So this recover the solution will be very nice compared with the pins, because the original 4 pins cannot catch this singularity well. But this adaptive sampling strategy can get this singularity very, very clearly. Okay, this we also compare with this DAS. It's another state-of-art algorithm. So basically, because the DAS is a different adaptive strategy. So we just concerning when we're adding the catching on the same number of the sample point, like a 5,000 sample point. The error for pins is -3, and for DAS is -4, and for our method it's -5. It's the error decreasing a lot. Okay, then we can see the 2 peaks problem. If we can, this is a 2 peaks problem. Here is the exact solution. We have the 2 singularity, and here. Okay, of course, this again, this is after the y iterations, this adding point. Okay, now this is the total point is 1,000, and after the 4 iterations, now the total point is 2,500. This adding point are concentrated on this 2 singularities. And this after the 9 iterations, now the total point is 5,000. Okay, we can find all the ending points in the red color are just concentrated on these 2 points, on the 2 singularities. So it can catch the singularity well for this 2 peaks problem. Okay, after the 19 iterations, so the total sample point is 10,000, which is the error is very small enough. Again, this is a comparison with the gas, but we have the 2 type of the gas, which is one is the globally, we just pick up the Ng, the largest residue. Another one is we need this the point are separated, well separated. We call the local maximum. Okay, so we'll find this local maximum since will have some smaller have the better performance. It's easy to understand, because if we using the global things to catch up this to add the point, it's not as efficient as the local way, because most likely there's only the 2 singularity, most likely at y iterations is adding all the points on the 1 singularity, and the next time go to another singularities. Okay. Most likely. All right. Now we concerning more complicated problem with the 9 peaks. Okay. So 9 peaks is just like that. We have 9 singularities, and it's all the similar things after the 4 iterations. Okay, the 4 iterations, we add in point like that in the focus, concentrate on these 9 points. And if we have the 9 iterations, okay, looks the adding point in Riccati is looking like that, and the reconstruction is well, right? Okay, this 19 iterations, all the point is 20,000, and this adding point on this similarities here. Okay, so we can see this the proposed method is can capture the multiple singularities. Okay, because when we do the adaptive sampling process, when this singularities, we added the point nearby these singularities. Okay. And after the 19 iterations, the error is becomes -5, 10 -5. Okay. Next, we test more complicated with Berger's problem, which is a line singularity. Is not a point, not only a point singularity. It's a line singularity. Okay, this is pins and okay. So here is a line singularity because this is a solution. Okay, this is the x race is the time and the y race is the x. Okay, so we have the line singularity here. This is a line singularity. Okay, for the line singularity, we can find this is the first iteration. So we add in the point is already is okay. It's just nearby this singularity. Also nearby the interval, the initial line. Okay. So after the 3 iterations, so all the adding point is on this straight line and nearby this initial time. Okay. So this is all the ending point. And also this is the 5 epoch. Okay, this is all the ending point is on this line singularity there. All right, so we can find this proposed method can localize the line singularity of this the x-axis. All right, and the error after the 5 round of the adaptive sampling is 10 minus 5, which is at the 5 iterations, which is the total the number of sample points is 20,000. Okay. Now let's test a high dimension problem, which is a 10-dimensional case. 10-dimensional case, which is the solution itself is okay. Is still the single the point singularity, okay, but in the 10-dimensional space. So we're using the relative error here. The relative error because it's difficult to draw the pictures, so we just give the number of the relative error. For this, if we have the 50,000 points, the basket error is 0.03, and our proposed method is 0.04. Okay, and when the point is increasing, our method becomes more efficient. Okay, this also we compare the result, the accuracy for our proposal method with FI pins. This is just a picture from the FI pins paper. Okay, and we adding the same number of the sample points. Use the 60,000 sample points of the sample points in for FI pins is like the 10 minus 1. For our proposal method, we get 10 minus 2. Okay, the last picture is to show what is the how do we choose this ng, the number of g, how many the how many in the mixing of Gaussian. Okay, from this picture, it looks like when this ng is large, it seems to be better, but not exactly to be true, because in our RQ paper we have another picture which is 20, 40, and 60. We can see the 60 is not the best. Okay. The best is sometimes 20, sometimes 40. So to how do we adjust, how do we choose the ng, the number of the mixer Gaussian is also not easy. It's not easy. Okay. Right. So here is the way to show the different choice of this NGs. But if we choosing the NGs relatively large, it can be bad. Right. So let's make a conclusion. So in all this talk, we develop a Gaussian mixture distribution-based adaptive sampling strategy. And after we have this adaptive sampling method, we just using the pins and using the same way, just like we have the cost function, we have this sample point, we just using the stochastic gradient descent to train, and all the other things are same as pins. Just the only difference is we just do this adaptive sample strategy. Okay, the key idea is we just assume this distribution is in the set of the mixture Gaussian. Okay, then we adding all the points followed by this rule. So we can find this to determine the coefficient of this Gaussian mixture. We use the location of the maximum of the residue. Okay, that every people use. All the previous work used, but we also use the derivative of the residue. Okay, that is to make this better. So with compare with some of the existing type of sampling method, our proposed method is easier to implement and can get the better result. Here is a reference. Okay, it's on the archive already. If you have the any there's more details in this the archive paper. And thank you.
Thank you, Professor Lu. Do we have questions for him? Yeah, maybe I can ask. I had a couple of questions which I could ask you. So,
okay.
So when you said that you started with a less dense mesh, did you see any change in the in your number of iterations or developing like having more or less adaptive points if you started with a little dense mesh, like little dense number of points?
Okay, you mean this? Let's look at this algorithm there. Yes, more details. Okay, so in the let me see number. Okay, you mean the initial mesh or this every time with initial mesh? Yeah. For experience, the initial mesh doesn't matter because the initial mesh, okay, initial mesh is just like the uniform data, okay, uniform distribution. When we have even have a lot of uniform distribution, it's not nice because it's not efficient. So the initial mesh is we just have the reasonable number of initial mesh is enough because initial mesh is to run the pins and we get the residue. That is the task. Then let the iteration go. It's not necessary to get a very fine mesh. In all test is just like a 500 in the 2 dimension.
What was the percentage of the NG? Like how much total number of points did you select after for the residual for getting the residual adaptive points? What was
okay? Okay, for the most examples, we set NG is 20. Okay, but for 9 peaks, we set NG is 40. Okay, we said we need more Gaussian mixture, and for each Gaussian, we using the 25 because we added 500 points, so 20 times 25 to estimate the parameter in Gaussian. We need some point to estimate the parameter in this Gaussian mixture. So in the most cases we use is NG, but for high dimensional it's different. Also for different problem we use a different setting. But for the easier problem, the NG we just fix as 20 and the point is like the 25 things. But for this complicated problem like have more peaks, the Gaussian mixture may be a little bit. We need a more Gaussian mixture, and for the high dimensional problem, we need more points to estimate this the parameter in Gaussian mixture.
And one last question which I wanted to ask you is like when you had for a particular iterations when you got got some adaptive points, did you rerun that iteration or did you move to the next iteration?
Oh, we keep them.
Okay.
We just keep we adding the point. We always adding the point. All the old points are kept in the iteration.
After you added the points, you rerun the particular epoch, like particular iteration, or did you move to the k plus 1th iteration?
Keep them. Always keep them. Always keep them.
Do we have more questions? Okay, if not, thank you, Professor Lu, for this presentation.
Okay, thank you.
We'll wait a bit for our second speaker. He's not online yet. That's why we wrote to you. So, could you try like sharing your screen when I introduce you to the audience?
Sure.
So our next talk is by Dr. Efstratios Gavves. He's an associate professor at the University of Amsterdam. His research focuses on the computational understanding of time, dynamics, and causality. On this, he pioneered the dynamical video representations in visual spatiotemporal data in 2014. While in 2016, he introduced the paradigm-shifting Siamese algorithm in visual object tracking, challenging the 30 years of practice, which is now adopted virtually as the state-of-the-art. Since 2021, he has spearheaded research on causal representation learning for algorithms that learn autonomously by integrating cause and effect to its core. His research on computational learning in time was as that he was awarded the ERC Career Starting Grant in 2020. And also he became the director of QUVA Deep Vision Lab with Qualcomm. Today, his presentation would be accompanied by one of his students, Liz Auzina. She's a PhD candidate at the University of Amsterdam on modeling dynamical systems. And she is co-advised by Dr. Sarah Meligan. She is a visiting scholar in Professor Matthias's lab at Tübingen University. Before that, she obtained her master's degree in the University of Amsterdam on approximate Bayesian computing for discrete data with Professor Jacob, and also was nominated as the Best Master's Thesis Award. With that, please join me in welcoming both of them for the presentation. You may want to take it away.
Thank you very much for the introduction. Let me see if I can minimize my windows so that it doesn't disturb the screen. Yes, I'm really happy for the invitation. It's really great to be talking to your group and your university, very renowned one. Indeed, I'm going to discuss today about my latest research on foundational dynamics, what I would call foundational dynamics, also in the spirit of times. And I'm going to start, or we're going to focus from the Invariant ODEs work and continue with the latest work on mechanistic neural networks. For the IIze will also, who is the lead author, will be describing the algorithm. So very briefly, who I am, I'm an associate professor on deep learning at the University of Amsterdam. I have been, I have received the 2 top prizes in Europe and Netherlands, something similar to NSF Career Award, Starting Career Award, the ERC Starting Grad and the VD, on roughly the topic being the learning of time and dynamics in vision. I co-direct 2 labs, CUVA and PopArt, with Qualcomm and the Netherlands Cancer Institute and Electa. My team, TILDE, comprises of 15 PhD students and postdocs. I'm a scholar of the ELS European Lab on Excellence in AI, teaching deep learning 1 and 2 at the University of Amsterdam, and also have co-founded a spin-off, a university spin-off, Elogon AI, for extending AI for oncology and immunotherapy. My research interest focus is centered around temporal deep learning, what I call temporal deep learning, which I believe until recently was let's say, under observed in the literature. And more specifically, I'm focusing on 4 pillars: neural dynamics, so understanding the dynamics of neural networks, as well as learning dynamics with neural networks, the applications of it to AI, like of AI into science, as well as how this is extended to computer vision, which is my original research field, computer vision. embodied vision is also about dynamic environments, and causal representation learning, which is a theoretical framework for embodied vision, at least in my perspective. So I would like to start with what I observed the last few years as the golden age of learning algorithms. Why I'm starting here, because I think this leads to why time is interesting. So the golden age of learning algorithms starts ever since 2012 with the introduction of AlexNet, which beat the ImageNet challenge in 2012. So for those of you who were back then busy with AI, we were working on AI. In 2008, we had the Pascal VOC challenges, the precursor of MS COCO. The scores that we were getting there for segmentation detection were roughly 32 points of mean average precision. We were considering these scores really high. We were very happy about it. Now, segmentation and detection, at least in computer vision, I would say is considered to be solved, or not necessarily solved as in the numbers are perfect, but we know the recipe, we know how to make it better, and you just need more data, more compute, and usually it works. But the golden age had more. We can do image captioning or video captioning. So basically, given an image, start describing what is in the picture in an uncanny fashion, right? Like it's extremely impressive what can be done, especially now with ChatGPT. We have face generation, so generative models, generative AI, which is all the rage, especially now with diffusion models. Producing extremely high realistic and high dimensional inputs or outputs, actually. We had algorithms beating the 18 times world champion in Go, Lee Sedol, and we had algorithms actually solving the protein folding challenge after 30 or 40 years. So what is extremely relevant and interesting for deep learning here is like for the talk here is that all these challenges, all these tasks share the same algorithm, the same framework, deep learning, neural network. So basically with a single type of algorithm, we were basically able to solve or to address, at least at a very good level, like decade-long problems, standing problems, which is quite amazing, like one algorithm that rules all. And what makes it even more interesting is that, well, there is an urgent paradox, which basically fueled my proposals a few years back, in that modern deep learning ignores time. So I studied computer vision. I was working a lot with videos, action recognition, action classification, action detection, tracking, everything, whatever, like moving things in general. And I realized, as well as others realized concurrently, that videos, whether they're reversed, shuffled, or normal, it's irrelevant for the AI algorithm, for the deep learning algorithm. The AI will give similar results. And of course, we're talking about the, let's say, vanilla deep network. Of course, one could make hacks, can make specific choices to guide the deep network for a specific problem. However, in general, the deep network was actually ignoring time. And if we would literally shuffle the frames, we would get very similar action classification performances. Now, for some, that would be a feature, right? Like it gives you good action classifications, even when the video is shuffled. But in my opinion, this doesn't make sense. You know, it should not work. Like higher accuracy is not always the desired outcome here. And what is very important, in my opinion, is that real-world data, especially in sciences, and real-world tasks are largely spatio-temporal with a very strong temporal structure. So it's very important to be able to recognize temporal, like to be able to address temporal tasks because they're basically all around us. And without it, we cannot do prevention, we cannot anticipate, we cannot extrapolate. Luckily, and very happily, the literature in the last few years also spotted this to a certain degree. temporality dynamics are becoming very, very relevant, very important. Your university, your groups pioneered with the same work on physics and fault neural networks, showing how deep networks can be extended to model temporal or spatial-temporal scientific processes. Symbolic regression with Cindy, although it doesn't use a neural network, it relies on regression. Still, it shows how temporal sequences can be successfully modeled. Of course, we had neural ODEs a couple of years back, which like a paper that won the best paper award in Europe. And yeah, it was a very interesting, very fascinating approach that looked neural networks as ODEs or Hamiltonian generative networks that try to embed Hamiltonian formalism to the latent space of neural networks, to the image manifold, to the video manifold, and so forth. So temporality and dynamics are becoming more and more relevant. And in my opinion, what is really missing right now is how do we scale? How do we make it bigger and better, more generalizable, actually, on real data, not just on synthetic data that I have also been working on in the last few years. So my vision, in a way, I would describe it very briefly as I would like to have an AI which is autonomous and physics aligned towards foundation dynamics. I think a good analogy intuitively is ChatGPT as well as the robots by Boston Dynamics. What one can observe from the popularity of ChatGPT is that not that it's accurate per se. In fact, quite often it gives a lot of incorrect answers, but the fact that it's very generalizable and it extrapolates quite well. Of course, the question, what is extrapolation, is relevant, but for simplicity, let's say that the fact that the ChatGPT can answer any question from 10 million users without really breaking, it doesn't give absurd answers. It might give wrong answers, but it doesn't give absurd answers. I think that's what impressed people, and that's what fueled all the hope. Now, what I mean by autonomous and physics-aligned AI is I would like to have something like that for instance, robotic agents or autonomous agents that operate in the physical space, that can operate in a so like with physics involved around it, learn representations of the world, be able to interact, learn cause and effect, and so forth. And I would like, when I say analogous, I don't mean take ChatGPT and put it in a robot, but more like, how can I create such an algorithm with which I can interact, like the robot would be able to interact with the environment, would be able to understand and correspond without failing catastrophically. And how this can be done, my hypothesis is that with multi-scale, multimodal, high-dimensional space-time data, there is shared temporality, shared causality, shared dynamics that can be leveraged towards autonomous and physics-aligned AI. I think, for instance, that for a robot to be able to generalize, like if I throw a ball to the robot, like the ball, like the robot should be able to capture the ball. So it should follow the trajectory of the ball. Now, the canonical way of doing that right now would be learning to predict future frames. So painting pixels, basically. I think this doesn't make sense. I think it makes much more sense if the robot, if the algorithm has an innate understanding of the physics, not necessarily reproducing them, but understanding them, like being able to align to them and extrapolate. I think that this is very important. So extrapolation, in my opinion, is very important. Like that's the main point. And to do that, I believe learning the dynamics, so not just imposing them, but fusing them with data, as well as learning causality, cause and effect, are key. I believe that once we have that, or even before that, we can reuse the same findings, the same methodologies, the same ideas for AI-powered science and engineering. I don't mean that, of course, all the methods would work perfectly everywhere, but in my opinion, once we are able to, for instance, model the physical space around us with the ODEs involved, with the PDs involved, and so forth, quite likely we would be able to reuse much of it to model much more precisely, well, not much more precisely, but much more precise tasks like scientific tasks or engineering tasks. And yeah, maybe here foundation dynamics would play a key role. So in this talk, after this introduction, in this talk, we'll be focusing with Ilse on neural dynamics. So she will be discussing about the modulated neural ODEs and AI and science. Modulated neural ODEs was a work which is currently in submission and also on archive by Ilse Auzina, Çağatay Yıldız, with Max Planck Institute in Tübingen, Sara Malakane, colleague at the University of Amsterdam, Matthias Bethke, also in Tübingen, and myself. Now, a summary slide that describes the general idea before I give the floor to Ilse about this work. So we want to model basically time invariance and time, let's say, variations. The main goal is to learn dynamic models that can extrapolate to infinite time horizons. So for me personally, having a model which models temporality only within the narrow confines of the time horizon seen during training is not good enough. If you cannot extrapolate, there is not much point let's say not that there is not much point, but it would still be a very limited model, because at least theoretically you could build a static model to do the task itself as well. So the main goal is to have dynamic models that can extrapolate to infinite, in quotes, time horizons, or at least much longer than what has been seen during training. And the root cause hypothesis for this work is that in high dimensional data, which is our interest, so videos, and by videos, it can be a lot of things. It can be videos of, computer vision in the computer vision sense, or videos of, for instance, scientific recordings. So the root cause hypothesis is that in high dimensional data, like we have an entanglement between time dependent and time independent signals. And these two different sources of signals have different statistics. So treating them with a, let's say, monolithic model is not the way to go. So our key idea here is to separate this time invariant from time invariant latent somehow, and modulate the learning. And in this work, we managed to, or we propose such a model, which we validate successfully with various spatial-temporal problems like oscillating systems, videos, and human trajectories, showing the generality of their work. So it doesn't work only on, let's say, perception data like videos, but also in scientific recordings. Ilse will now give the overview of the method, and then I will continue further on with the talk after she finishes.
Thank you for that introduction, Stratus, and thank you everyone for inviting us. I'll take over the screen share as well on this. So I think everyone should be able to see my screen. So also initially you invited us under the paper of the title Invariant Neural ODEs. And already Stratus mentioned this is a joint work actually by University of Amsterdam and our collaborators in the University of Tübingen. And Stratus already gave you some details, but I'll go in a bit more depth of all of it. See? Yes. So the first question is like how we came about this paper, or how we came the idea for this work. And indeed, we came about coming from this question whether setting apart dynamic states from underlying static factors of variation might improve the existing model performance. And what we mean with underlying static factors of variation is indeed if in a setting, for example, where you have a video recording of, for example, a pendulum like this, you can imagine that, this pendulum might have length and mass, right? That actually doesn't change in time or with respect to recording, right? And at the same time, if one of the goals of your task is also to reconstruct this video or this image you see. Also, the color of the ball or the background or the color of this stem is basically time invariant, so it's static. Similarly, you might have, video recordings of, let's say, humans or human behavior. And at the same time, also here, right? Here, we would have length of limbs that are invariant as such. Or you could also mention, for example, I have to move this somewhere, 1 second, and my apologies. Yeah, and the color of the clothes. And as you can see, like these variables have some relations with each other. For example, the first part that I mentioned, these are static factors of variation that actually influence the dynamics. But you can imagine that the length of a person's limbs or legs is going to affect its basically walking speed or the type of walking. The same as here, the length of the pendulum is going to affect the frequency of oscillations. Similarly, the color of the clothes or color of the ball is going to affect the reconstructions. So at some point, as we were discussing this, we actually decided that we want to rebrand the names of the paper, because as these variables are time invariant, actually their main functionality, or how we introduce them in our work, is via naming them modulator variables. So to some extent, they modulate either the perceived, the final perception of the object that you're modeling, or they actually modulate the dynamics that you're basically the underlying dynamics of the system. So what you can see here is a schematic illustration of our method. And the main idea is that you have some observations of the sequence or images, right? And traditionally, we have like this in, let's say, neural ODE framework. If we modeled in latent space, we have some encoding vector that brings us to a latent state embedding, initial state. And then we do this in this latent space, this forward simulation with a neural network being our differential equation using given solver. And then we have a decoding network that maps it back to observation space. And what we propose is what you can see in red. Basically, we propose that from this input, you actually can use a modulator prediction vector network that is going to produce you two types of modulators, dynamics modulators and static modulators. So dynamics modulators are going to influence dynamics. And as you can see from the previous slide, you can think of them as, for example, length of limbs or length or mass of the ball of the pendulum. While static modulators are going to only affect your decoding network. So that's really the appearance of the object you're modeling. So as that, we rebranded our paper to modulate the neural ODEs. And let me now, I think, go immediately into further details of this. So first, I want to describe to you the generative model. So assuming that we already know these variables or know from how we're modeling them. So in principle, right, we sample from some distribution our dynamics modulator. Similarly, we have a static modulator. Then we have the latent ODE state, right? That let's basically represent some coordinates in latent space. And what we say is how we adjust the existing works and how we basically what we introduce this different generative model is that we say that this dynamics modulator comes here as additional input to the differential equation that you model with a neural network here, while the static modulator comes here. P of xi is some decoder network where it also comes to concatenation. Now, this is the generative model. The question is, how do we actually learn these latent modulator variables? So first, we're going to focus on the static modulator. So if you think of the graph that I showed you, to the bottom part of the network architecture. So basically what we want to do is we want to compute an average over the observation embeddings. So you can imagine, so actually read this equation from the right-hand side to the left. Here, n means a given trajectory, and basically I means that like this is the temporal point. So in principle, you might have like t of these sequences of the nth upward trajectory, and g is some encoding network with psi parameters. So you can imagine this could be like a convolutional neural network. And you just pass your input in data space via this convolutional neural network, and you obtain this latent embedding. But what you have to do on top of that, right, is that we say we want to obtain this time invariance. And one really simple way how you can obtain this, right, is simply average over the time points. And as such, right, we then obtain for all time points, we obtain this latent static modulator variable for this specific trajectory. Now, how we use it once we have computed it, right? Then we pass it to this decoding network that is depicted here, right? And there simply we can concatenate it with a latent ODE state that's been produced with the solver. And then we map it back to the data space. Now, on the other hand, we have the dynamics modulator. So the upper part of the network, as you can see, it's quite similar in the sense that, again, we take it from the input data. Here, the main difference here, right, is that dynamics modulator, you need to compute over subsequences of length TE. You can think of this as an example. If you would like to compute, for example, in the context of the pendulum, the length of the string is a dynamics modulator. In order to compute this, you need to estimate acceleration, but of course, you cannot estimate acceleration from a single frame. You need subsequences of multiple frames. So hence here, you compute the embedding. Again, H is some neural network. In this case, probably you would use like a recurrent neural network. You have the temporal property of the data. You obtain, again, a dynamic for this given trajectory. And again, to obtain a time invariant, basically latent dynamics modulator, you again average it over the subsequences that you have obtained. Now, instead of passing it to the decoding network, now you're going to pass it to your actual differential function as an additional input. Now, what we mainly want to emphasize that what we propose in this work is a general framework. So meaning we're not introducing per se a new model, but more like a way of modeling. So what I mean by this is that this, let's say, central part of this is actually could be most neural ODE models. And this is also what we show in the paper, that you can use a latent neural ODE model here. You could even use a second order neural ODE model and actually model it in data space, meaning that you don't have like this encoding network. It could be a latent second order neural ODE, or it could also be more recent work such as heavy ball neural ODE. Because basically, yeah, it can be applied to most neural ODE, and it also shows its versatility. And most importantly, right, whenever you introduce something new, the important part is that it improves performance. And this is our in practice. So first, of course, you test on some synthetic data. And in this case, for the sinusoidal data, right, we only have, let me go back to here. In this case, right, we only have the dynamics modulator variable, that upper part, right, because your observations are just actually, let's say, the XY coordinates. So there's no need for a static modulator. So for sinusoidal data, this is exactly what Efstratios a bit discussed beforehand. So which I show here on the left-hand side are 3 trajectories on the test data. And so basically these are amplitudes and frequencies that the model has not seen during training. The shaded area is what the model is conditioned, or the darker gray area is what the model has seen how far during training. So 15 time points. And what we do simply here is ask the model to predict until far future. So in this case, 150. And especially where you have like this lower frequency domain, you can see that the model really kind of basically, right, in some sense, this is a conserved system. The energy should be conserved in the system, but the model does not have this property, and it simply wanes off and is not actually consistent. Now, with adding our framework on top of it, which we call modulated neural ODE, we can see a massive benefit of the system. So we can actually see that, and like, so the multiple lines is basically that you have multiple draws of the system of the model itself, because underlying you have to sample the initial state. So you can see that our model actually massively improves the performance. And actually what is most interestingly, we also examined how we could explain these results. We examined the latent dynamic state of the system. So here in the upper corner, you can see the latent state. So this is a PCA decomposition, because I think our latent state in this experiment is 8-dimensional. So we map it to 2-dimensional state so we can visualize it in 2D. And here the colors that you can see here match the colors of these 3 trajectories that are like depicted here. And for the neural ODE model, we can see that actually these latent embeddings are not really meaningful, or they don't represent, at least from like this visual evaluation of it, doesn't represent any properties that we actually observed in the data space. While for modulated neural ODE, we can actually see that the relation or topology of these amplitudes that we observe in data space. So let's say the trajectory 14, or the blue one, has the highest, while trajectory 7 has the smallest, has actually also now been captured in the latent space, also explaining why we see such an improved performance of the model. Similarly, we also test our model on more like complex data. So as you can see in the page over predator-prey data here, just for an example, I'm now showing the results with heavy ball neural ODE. In the paper, especially in the appendix, you can see the results for all the models mentioned on my, let's say, 2 slides ago. And again here, doing the training setup, or like, again, like, so this is on test data where the shaded area is conditioning, the gray area the model has seen, how far it has seen during training. The model fits the data extremely well. You could almost say almost perfectly, right? But immediately once we go beyond the data points or the trajectory length that is seen during training and try to extrapolate, this model massively overshoots. Now, and I think here the results are even more stunning by just simply applying our framework on top of it, by separating these dynamic states from like the static latent states. We see a massive improvements. And again, similar comparison here with respect to the latent space. Again, we can see that. So here on trajectories, you have to keep notation that in the previous slide, they had all the same scale. Here, the scale on the left-hand side is different. So meaning here, the trajectory blue one is until 40, which also maps with the observed learned latent space, while the orange and green are quite similar, with the green one being a bit smaller. And you can see this relationship also in the latent space for our model, while for this original heavy ball neural ODE, you haven't captured this property. Yeah, so as this both results have shown, multi-layered neural ODEs improve performance with respect to forecasting and generalization. So here, just I showed you only visual examples, but also to show you that, let's say, mathematically based on test mean squared error, our proposed model or framework on top of the existing models improves all of their performance. Both, let's say, on generalization, just on new test sequences. So when I say this means basically models with different underlying parameterizations, as well as on long-term forecasting, actually, the improvement is massive. And more so interestingly, right, so as we absorbed in the previous slide, or both previous slides, we had like this nice finding that if we examined actually the embeddings of our latent states, we actually had this nice property that actually it seems like it shows something meaningful of the observed data. So we wanted to test this more, let's say, whether this also, we can show some proof of this mathematically, not only, like, say, visually. So indeed, we would like to, a soft claim that we also improve disentanglement, because there's a whole field of disentanglement and how it's done. So we don't want to, let's say, say anything wrong, but we computed our, so basically we regressed, we took the trained models and then regressed basically for neural ODE model, just latent dynamic states, and for modulated neural ODE, basically the dynamics modulator variables with respect to the true unknown factors of variations. And here a higher value would indicate a better performance. And we can see that for our model, it's better with respect to design, predator-prey, or bouncing balls data set, meaning that our model is better on disentangling these factors, also having some, let's say, a conceptual mathematical proof of the observations that we have seen in practice. Now, of course, it's nice that when your model works on simulated data, and we want to also test it a bit more on realistic world setting. In particular, what you could put it on, we tested on like this mockup data set. We have trajectories of walking human basically patterns at 50-dimensional. And particularly, we tested 2 setups. One mockup, basically the model sees all the training data, just some trajectories are taken out, or mockup shift, what we call here, is specifically one participant is taken out from the data. So you have never seen this person in your training data. And again, here we can see that, and in this case, in this setup, we use both modulator variable static as well as dynamic modulators, because you can imagine that, for example, in this case, the length of the spine, or let's say the width of the shoulders would not really affect the underlying dynamics that you're trying to see, but would affect, for example, the reconstruction quality. And second, you can see again in this, like with respect to test MSC, that our model again obtains an improved performance. So the key takeaway that we wanted to say with this model, or this with the modulated neural ODE paper, is that we introduce a modulator framework that allows you to separate time evolving ODE states from modulator variables. And the benefit of this is that you can express now constants as modular variables, meaning rather than specifying a new network for every different parameterization of your function, you can just add it as, let's say, a variable that affects your dynamics network. We showed empirically that improved generalization as well as for horizon forecasting. And with respect to this R2 score, that also captures true unknown factors of variation. So the limitation extensions of the present work is, of course, at the moment, the experiments you've done, and also this paper is limited to deterministic systems. Of course, in reality, you might have stochastic processes, which also makes the far horizon forecasting more difficult, but it also, I think, opens an interesting avenue of how you can model these modular variables if they change also over time. Perhaps you also want to have a network that infers them, or different approaches to this. Secondly, to this also, you could say at the moment, how we model the modular variables is as point estimates, rather, and then of course you might have this issue that when your modulators are out of distribution. And I think a nice interesting application here would be switching it to more a probabilistic or Bayesian approach. We actually model them as distributions, and also actually then you can change the way how you would like to infer them. So we just use this kind of very, some say, simplistic approach, just averaging over time. There's nice work by Mark van der Wilk on learning such like invariants using marginal likelihood, which might be a more, let's say, theoretically grounded and also a more Bayesian approach, which might be an interesting extension of the present work. Second, and I think this is a very nice third point, which is a very nice point, is that so when we computed these latent states of the variables, we actually, with respect to the loss function, so the loss function we used was just the same loss function that was used to train like latent neural ODEs or most the neural D type models, so it's evidence lower bound. So we didn't have an explicit term that would enforce that these latent dynamic states of the neural ODE and these modular variables, that actually they should capture different information, or that they should vary. But by fact, actually it happened by default of the framework. But we assume that perhaps that if you would include also self-supervised contrastive loss, that also would push these representations in a latent space to have more different representation, might also be advantageous or could be extended. And lastly, our work goes in direction also interpretability and disentanglement. And of course, we only touch about it like softly because also it wasn't the main focus of this work. But I think given the latent representations we obtained, this could be extended in some settings where you really want to learn the underlying variables or underlying properties of the variables. That might be an interesting avenue. Now, as I mentioned last, I think my last slide is more, let's say, looking into the future. As I say, what we propose is a framework. And in this case, for this paper, we applied with, let's say, well, neural ODEs for modeling the dynamics for this type of models. But I really believe, or it's also where we're looking in the next steps, is that this modulated framework can also be extended to other models that currently don't capture such information. So one of this application, for example, is a research or large research field in object-centric representations, right? You might have seen like these, like, let's say, videos or models that kind of learn a representation for every, let's say, object in this frame, and basically also try to model how they change over time. Of course, in reality, every object could have different friction properties, different mass properties. And at the moment, there is no way of how to model this explicitly, right? It could be that actually all these models follow the same like physical properties, simply their friction or their mass is different, thus adjusting these physical properties. So I think it's a very interesting avenue to proceed with this. Similarly, we're also interested in a bit more, let's say, in biology applications, where, let's say, in this left-hand side, we're thinking here, right, in, let's say, in wildlife conservation, they often have the issue that they need to like re-identify an animal, which is often quite hard to do. But in similar, as we in like this last example that I showed you with the human walking, where we would learn a specific static content variable for every person, if the model will be able to learn such a representation for every animal, maybe it would make it easier to identify it, and also here in right-hand side to track it over time when they're also occluding each other. So all in all, I would like to highlight once more that I would like to thank all my collaborators. So it's here you have all the pictures of them: Trishchata, Yildiz, Sara, Maklikana, Matthias Betke, and of course my supervisor in Amsterdam, Efstratios Gavves. And yeah, thank you for inviting us for the talk and for having the time for us. And yeah, thank you for your attention.
Yes. So Yeah, thanks, Ilse. Now, in the remaining time, I will briefly discuss about another relevant work in the same space, which might be of interest to you. Now, this work has not been published in our archive yet. It's in submission. Hopefully, we'll upload to archive also quite soon. It's joint work with Adil Pervez, who just finished his PhD and about to graduate, and Francesco Locatello from Max Planck Institute in Tübingen also. And that's just a coincidence. I don't work just with Tübingen. I find this work particularly interesting because basically it addresses a fundamental challenge of neural networks, and it also relates to physics in form models, Cindy, and so forth. So basically, neural networks at their core, they simply output numbers. So they're just like they're a function fitting process algorithm who receives as input some data. It can be trajectories, like in the top left corner, or a time series, so like numbers over time, or it can be even static datum, like a picture of a horse in this example. You know, we take like any of these inputs, we pass them through a neural network, and the output is always a number or a vector of numbers or a collection of numbers, but always a number. Even when plotting outputs as functions, like what we saw with invariant neural ODEs, they're still somehow a number. In this work with mechanistic neural networks, we challenge this assumption, and we propose a neural network that returns mechanisms, that returns functions. This is similar to what Cindy has been doing, but Cindy is constrained to regression, so symbolic regression. It doesn't really use neural networks and the power of them. And so with mechanistic neural networks, we generate governing equations. So the neural network is, so this is, let's say, the neural network definition. And the UX is the output of the neural network. The output takes the form of an ordinary differential equation, linear ordinary differential equation, like here, whose parameters, whose coefficients here, C, K, and B, are governed by the neural network. So the neural network, the role of the neural network is to return the coefficients of the ordinary differential equation that defines the layer output of the neural network. Now, what is interesting here is that the proposed model, mechanistic neural networks, works for any type of data. So it can be time series, trajectories, or it can be even horses. So the model, the mechanistic neural network, will return an equation of the picture of a horse. Right, so it is different from Cindy because it basically integrates the equation estimation, the equation estimation within the neural network. So it's not just a regression on features. It's also different from neural ODEs in the sense that neural ODEs basically, you know, the model itself is an ODE. The neural ODEs treat the neural network as an ODE, whereas mechanistic neural networks define outputs to be the ODE, to be the function. So the point here is that the result of the neural network is a function itself. Right, so in this picture, for instance, we would put like the picture of the horse, and we would get like this ODE that theoretically describes the picture. Now, how does this work? It's a bit crazy. So the key ideas here is as follows. First of all, we make the observation, or actually it's an observation from the 60s, that solving a linear ODE itself can be written as the solving of a linear program, like min-cut max flow. And as a matter of fact, in IClear 2023, presented in May, we presented a paper on differentiable mathematical programming for object-centric representations, which posits that one can integrate the solution of a linear program as a forward propagation in a neural network layer. So the layer of the neural network becomes the solution of the linear program. This is similar to some other algorithms that have been proposed a couple of years back. But the difference here is that we are making a relaxation of the linear program, so that we don't have a fixed point solution here. Instead, we're solving a linear program. A third key idea here is that we relax the linear program. We show that we can relax it to a differentiable quadratic program. And this is important because then the problem becomes, well, it's differentiable. So it means that we can backpropagate through it without problem. And in turn, this allows us for fast parallel solving in GPUs. So we can solve the linear ODE in a batch and in one shot, so to speak, contrast to the sequential approach of parallel solvers. Importantly, while the function definition is a linear ODE, an abstract linear ODE that we have to define in advance. So in a way, you can say that this is an inductive bias. The coefficients that govern this linear ODE are returned by, are computed by the neural network. So they are nonlinear themselves. And that's why the mechanistic neural networks can also learn nonlinear dynamics. The computed governing equations can be outputs of the neural networks, or as a matter of fact, they can be outputs of the intermediate layers. So in principle, one can build a neural network whose every layer, instead of returning logits or intermediate activations, it returns literally equations, not values, but equations. And last, we are able to learn a governing equation per input. So for instance, for a specific image or for a specific trajectory. And of course, it will be very interesting to learn a shared governing equation, because quite often in scientific problems, we don't have one governing equation per input. But I think that this is not really a huge problem to address. Learning a governing equation per input is also an interesting, offers an interesting perspective in comparison with neural ODEs. Neural ODEs are learning, let's say, a single ODE that tries to model the data. With our approach, you can say that we're learning infinite ODEs, one per x, per input x. Now, on this work, very quickly, we did experiments on time series. So in the nested circles data, we were able to get quite good separation comparable to neural ODE variants. And on top of it, while neural ODEs wouldn't be able to, describe, let's say, in a compact form, the function that describes the data, this was literally the equation that we got describing a single data point for 5 steps. So basically, you can take then this equation, like this one here, and do whatever you want. You can plot it, you can analyze it, you can extrapolate to the future. You can even use it for classification. We also used it to learn physical quantities in a simplified 2-body problem. And on one hand, we see that the trajectories are pretty decent here. The starting time is here in the bottom right corner. And this is as time goes, the trajectories. We observe some deviation, but this is, basically in all these experiments, we didn't do any optimization at all of the neural network, of the hyperparameters or anything. I'm pretty sure that one could do a much better job here. Also, the conditioning here is just a single first time step. from there on, the model just predicts without any other prior knowledge. Interestingly, by making some reasonable, let's say, physical assumptions about the system. So, for instance, because we have a two-body problem, the ratio of the masses is proportional to the ratio of accelerations. We can plot the true and the learned orbital forces, and we see that actually the learned functions, the learned differential equations, are pretty close to what the reality looks like. Of course, again, this can be better. In this work, the focus was to like it was a proof of concept rather than explicitly solving a particular physical problem. However, we didn't stay only on dynamic data. We experimented also with images to see whether we can have a dynamic model that can describe them. So we trained an autoencoder, not a variational autoencoder, but an autoencoder for simplicity, where we use the mechanistic neuron layer as a bottleneck layer, and then the governing equation that the neural network would produce per image, we would evolve it through time, and we could take either the final state or intermediate states and then decode it. And as we can see, we get pretty decent reconstructions on C4, again, with very little tuning and optimizations and so forth. Much can be said on the applications here. I believe a fascinating direction, specifically on images, would be anomaly detection and alignment or interpretability. Whether, for instance, especially in video, can I extrapolate, can I plot out the function to see whether it deviates too much? You can do all sorts of tests, for instance, of the Lyapunov exponents to see whether the predictions diverge. So I think that could open the doors for quite exciting research. Now, other than that, a sample of related recent works to this talk. So with Lucas, we extend physics-informed neural networks for stroke, for brain stroke. We show that perfusion ODEs for blood flows, when implemented in a spatiotemporal way, has a really important benefit. So we can actually match or outperform commercial software like from Siemens, get much more precise blood flow estimation for finer structures, which is very, very important for brain strokes, like let's say small brain strokes that are not detectable normally. In ICML, literally this week, we're presenting graph switching dynamical systems, where graph networks we show that we can use we extend graph networks to automatically detect dynamics in complex and interactive systems, basically temporal clustering. And preliminary evidence show quite good like clusters in these dynamical systems. In causal representation learning, we're presenting next month Biscuit, which is the first method to learn causal latent variables in complex data like images. So far, causal representation learning is confined on either very low-scale, unrealistic simulations or on vectorized data, not on highly complex data like images. Neural computed tomography with neural fields. I think that's particularly important, or interesting, because neural fields are basically similar to physics-informed neural networks, save for the fact that they don't really use an explicit physical regularization. We show that integrating the physics of computed tomography to the neural network actually has also very important benefits, and also in terms of reconstructions, so less radiation to the patient. And learning group symmetries with neural networks. So for joint learning of one-parameter transformations of groups and distributions in latent observed spaces. So this was accepted in TAG-ML, also presented in ICML next week. And last, IClear 2023 on continuous convolution. So we showed how neural network can be used to define continuous versions of neural networks, which is particularly relevant for long-range computation. So especially when you got temporal data and you want to be able to basically estimate correlations between very long time steps, this is quite interesting. A shameless advertisement. Also for Deep Learning 1 and 2, we've got a lot of materials and modules and code for advanced deep learning topics like group equivariance, Bayesian deep learning, deep probabilistic models, causality, diffusion models, neural network dynamical systems, and so forth. In fact, our modules and tutorials have been featured by PyTorch Lighting tutorials. And I would like to close now. So in my opinion, temporality, dynamics, and causality is the next AI frontier towards foundational dynamics. I think it's imperative to do that in order to go to the next level. I don't think ChatGPT or the likes will be able to make it without some form of dynamics, temporality, and causality in them, because I cannot see how they can extrapolate. I don't believe that when we go beyond language, models can sustain learning all these basically innumerable correlations. And I believe works like physics-informed neural networks are an excellent example why this is the case. I have to say, personally, I'm much interested in collaborations on AI, dynamics, and science. So if you're interested, please let me know or drop me a line. And at the moment, we also have 2 postdoc vacancies in the lab on causal representation learning and embodied vision. And with this, I would like to thank you. And yeah, if you have any questions, Ilse and I will be more than happy to discuss with you.
Thank you, Professor Gavves. That was a wonderful way of presenting this. We really enjoyed it. So, do we have questions for both of them? In this group, we actually also started looking into integrating GPT-based surrogates with our with physics-based models. So we probably can have Varun, do you want to introduce your framework here? Do you want to speak about that?
Yeah, I mean, basically what I'm a PhD student at Brown. Yeah, what we were working on was trying to see if we can use ChatGPT to write pin codes. So that is like what we are trying to do. So the idea is that you provide a high-level interface to a user who can use it to write pin codes for solving like analytical problems in fluid mechanics, and not have to delve deep into how to write a pin code. So this is for someone like a layman who doesn't know how to code pins. It's a way for them to, it's a tool for them to use and, basically solve the problems.
Mean to transform the ODE or the PD of the problem, describe it in natural language, and then generate the code that
So one second. Our idea is that we are actually looking to train the language model so that it can recognize like certain problems, and then we train it with like code base that we have so that it can generate that code. So that's like a very initial. It's at a very initial stage. We're just like starting to see what we can do with that. But yeah, I mean, things like this, I don't think we're close to anything like this at the moment with GPT. So yeah, I feel this is very interesting. Thanks for the talk.
Yeah, thank you.
Do we have more thoughts or questions or any form of discussion for both of them? So if not, thank you for taking your time out and giving us this wonderful presentation.
Yeah, thank you very much.
Yeah, we will be posting the video of our recordings on our Crunch YouTube channel. So please feel free to check it out.
Perfect.
Thank you.
Thank you. Thank you so much for taking your time. With that,
Bye-bye.
we come to an end of our Crunch seminar today, and we'll see all of you next week. Bye.
Bye-bye.
Bye.